All right, here we go with our notes on 6-2 exponential functions. Let's begin with f of x and g of x, where f of x is 2x and g of x is 2 to the power x. Let's go ahead and construct a table of values, beginning with f of x. F of negative 3 is 2 times negative 3, or negative 6. F of negative 2 is 2 times negative 2, or negative 4. F of negative 1 is negative 2. F of 0 is 0. F of 1 is 2. F of 2 is 4, and f of 3 is 6. For g of x, we have 2 to the power x. So plugging in negative 3, we have 2 to the negative third power, or 1 over 2 to the third, or 1/8. Plugging in negative 2, we have 1 over 2 squared, or 1/4. Plug in negative 1, we have 1/2. G of 0 is 1, or anything to the 0 power is 1. G of 1 is 2. G of 2 is 4, and g of 3 is 8. So let's go ahead and graph both of these functions on the plane provided. So we have for f, we have negative 3, negative 6. We have negative 2, negative 4, negative 1, negative 2, 0, 0, 1, 2, 2, 4, and 3, 6. You can use a straight edge to draw on the line. And here is f of x. And let's go ahead and label that f of x. For g of x, we have the points negative 3, 1/8, and this you can just kind of approximate. It's really close to the x-axis. Negative 2, 1/4. Negative 1, 1/2. You can just put the point halfway in between 0 and 1. We have our y-intercept, 0, 1. We have 2, 2, 4, 4, 3, 8, and so on. So if we were to sketch in this graph here, consider what happens as x decreases. Take a look at our table of values. As x decreases, we get really close to a number. We have 1/2, 1/4, 1/8. If we were to continue, we would have 1/16, 1/32, 1/64, and so on. The numbers would keep getting smaller and smaller and approach a value. It would approach 0. So as you're drawing out your graph, make sure your graph goes really close to 0. But it never actually hits 0. We get really small, but we never actually reach 0. In the positive direction, the function increases and just keeps growing bigger and bigger. We go from 1 to 2 to 4 to 8 to 16 to 32 and so on. So let's consider which column is growing faster, 2x or 2 to the x. Well, that would be our function g. So I'm going to go ahead and label that. That would be our function g of x, or 2 to the x. As x increases from 2 to 3 in the table, what happens to 2x? Well, from 2 to 3, we go from 4 to 6. Or in other words, we add 2. As x increases by 1, what's the pattern? So every single time, what's going on in between each function value? We add 2 every time. Now for 2 to the x, what happens from 2 to 3? We go from 4 to 8. Or in other words, we are multiplying by 2, or this is times 2. As x would increase from 3 to 4, so we would go from 8 to 16, that would be g of 4. So from 8 to 16, then we're multiplying by 2 again. So then as x increases by 1, the pattern is for 2 to the x, we are multiplying by 2 each time. So times 2. So in your own words, why are the values for 2 to the x increasing faster than that of the values of 2x? Well, you can say that for 2 to the x, we are multiplying rather than adding. right? So our rate of change for 2 to the x is that we are multiplying rather than adding. So here we're describing an exponential function. F of x equals 2 to the x is an exponential function, whereas f of x equals 2x is a linear function. The difference between the two is that a linear function changes by a constant difference, whereas an exponential function changes by a constant ratio. Or in other words, a linear function has an additive rate of change. We're either adding or subtracting a constant amount, whereas an exponential function has a multiplicative rate of change. We are either multiplying or dividing a constant amount each time. Let's go ahead and graph another. So we have f of x equals 1 half x and g of x equals 1 half to the x. So f of negative 3, we have negative 3 times 1 half, or negative 3 halves. F of negative 2, we have negative 2 halves, or negative 1. F of negative 1, we just have negative a half. F of 0 is 0. F of 1 is 1 half. F of 2 is 2 halves, or 1. And f of 3 is 3 halves. For g of x, we have 1 half to the power x. So if we raise 1 half to the negative third, we have, it's the same as 2 to the positive 3, or 8. 1 half to the negative 2 is the same as 2 squared, or 4. 1 half to the negative 1, that's our reciprocal power, so that would be 2. Anything to the 0 power is 1. G of 1 is 1 half. G of 2 is 1 fourth. And G of 3 is 1 eighth. So plotting these points, let's start with f of x. We have negative 3 halves, or negative 1 and a half. Negative 2, negative 1. Negative 1, 1 half. The origin, 0, 0. 1, 1 half. 2, 1. And 3, 3 halves. So let's go ahead and use your straight edge, sketch in that curve. There, it's a line, so sketch in that line. And let's go ahead and label it f of x. Now g of x, we've got the points negative 3, 8, negative 2, 4, negative 1, 2, 0, 1, 1, 1 half, 2, 1 fourth, and 3, 1 eighth. So again, notice what happens as x increases this time. We're going from 1 to 1 half to 1 fourth to 1 eighth to 1 16th to 1 32nd, and so on. The function values are decreasing and we're approaching a value. Again, we are approaching 0 as x increases. We get really close to 0. So as you're sketching in this graph, go ahead and get real close to y equals 0. Now, as x decreases, notice the function increases. We have from 1 to 2 to 4 to 8 to 16 and so on. So as x moves to the left, or as x decreases, the function is going to go upward, or increases. And this is g of x. So let's go ahead and compare the two. Which one's growing faster? Well, between the two, g of x is decreasing, keeps going lower and lower, whereas f of x increases. So the one that's growing faster is 1 half x. As x increases from 2 to 3 in our table, f of x changes by 1 half. So we go from 1 to 3 halves, and the difference is we are adding 1 half. So then the pattern between each x, for 1 half x, we are adding 1 half each time. Now for 1 half to the x, what happens from 2 to 3? We go from 1 fourth to 1 eighth. So how does that change? Well, we're dividing by 2 each time, or we're multiplying by a half. So from 1 fourth to 1 eighth, you can say that we divide by 2. As x increases from 3 to 4, we go from 1/8 to, well, g of 4 is 1/2 to the fourth, or 1/16. And again, we are dividing by 2. So then the rule is, as x increases by 1 for 1/2 to the x, the pattern is we divide by 2. And I'm going to put a note in here. Remember, dividing by 2 is the same as multiplying by the reciprocal. So multiplying by the reciprocal 1/2. So you can also think of it that way. Divide by 2 or multiply by 1/2. Go ahead and flip the page. In general, for exponential functions, they can be modeled by the general form f of x equals a times b to the x, where a is non-zero constant and b is greater than 0 and not equal to 1. Therefore, if b is greater than 1, then we would consider this exponential growth. B is our growth factor. So that number underneath the x, the base of our exponential. If b is between 0 and 1, then this is decay, exponential decay. B is our decay factor. We can see a couple examples from our first two problems. So if you take a look at the first one, well, g of x, that base is 2. That's greater than 1. And you can see that this is growing. So this would be an example of exponential growth. However, for the second example, where we have 1/2 to the x, well, 1/2 is between 0 and 1, and you notice that the function is decreasing. This is exponential decay. The shape of an exponential function is either increasing or decreasing, but on one side it always approaches an asymptote. And we'll talk about an asymptote. So it's either increasing or decreasing, but on one side it always approaches an asymptote. And I've kind of alluded to what an asymptote is. If you notice for each of our graphs, on one side of the function, it blows off to infinity. It gets really, really big. But on the other side of our exponential function, it gets really, really close to 0. An asymptote is a value that the function approaches but never actually reaches. So if you notice g of x here, or even in the first one, as x increases or decreases, it approaches 0, gets really, really close. But the function will never ever be equal to 0. There's no number I could put in for x and have 1/2 to the x be equal to 0. It'll get really close, but it'll never be equal to it. And that's what we call an asymptote. It's a value that the function approaches but never ever reaches. Let's go ahead and identify some of these key features from the equations. So for letter A, here we have y equals 4 times 3 to the x. Now, the y-intercept, we know that the y-intercept is where x equals 0. If we were to plug in 0 into x for this equation, we'd have 4 times 3 to the 0. 3 to the 0, anything to the 0 is 1. We have 4 times 1, or just 4. So our y-intercept has coordinates 0, 4. Now, how could we tell that from the equation? You might notice that this number out in front, 4, is our y-intercept. That whole exponential piece here, this factor here, cancels out whenever x is 0. So all that's left over is our initial value. Okay? So this is what we would call, in an exponential function, our initial value. We can determine whether this is growth or decay by looking at the exponential base. Here we have a b value of 3, and that's greater than 1, so we know that this is exponential growth. The asymptote, what y value is this going to approach as x either increases or decreases? Well, in this case, as x decreases, the function is going to get really close to y equals 0. The domain, what are the numbers that we can plug in for x? Well, we can plug in any number we want. There's no number that we can't plug in. So the domain, and this is true for all exponential functions, is all real numbers. Lastly, the range, what are the numbers that we'll get out? Well, Notice that we never hit 0. This function will never be equal to 0. And likewise, it'll never be anything less than 0. We can't raise 3 to a power and get a negative number. Multiplying by 4 is never going to get us a negative number either. So we're only going to get the positive numbers. So the range is going to be all of our positive numbers, or y greater than 0. If we were to sketch in this, go ahead and draw in your axes. Some key points I want to see. So we start with our y-intercept. In this case is 0, 4. Go ahead and plot that point. We're looking at exponential growth, so as we move from left to right, the function is going to increase. As x decreases, we're really close to 0, so the left-hand side of your graph should be really close to 0. Lastly, go ahead and draw in that asymptote, the horizontal line on y equals 0. Draw that in as a dotted line to show that it's affecting the graph, but it's not part of the function. This is the function value. This is the value that the function approaches but never actually reaches. Let's try another. 5 times 1/3 of the x. Now again, our y-intercept is where x equals 0. Take a look at our initial value. This is 5. If we plug in 0 for x, all we're left with is that initial value. So our y-intercept has coordinates 0, 5. If you take a look at our b value here, we have 1/3. That's between 0 and 1. So we know that this is exponential decay. Again, our asymptote, the value that our function approaches but never ever reaches, is y equals 0. Domain for all exponential functions is all real numbers. You can plug in any value in for x. And then our range, this is exponential decay, but again, notice that this is entirely positive. There's no number you can plug in for x and ever reach 0 or anything negative. Therefore, our range is going to be all y greater than 0. Let's go ahead and sketch the graph. So draw on your axes. Our initial value is our y-intercept at 5. And this is exponential decay. So from left to right, your function should be decreasing and approaching 0. So just a quick sketch. Go ahead and draw on that asymptote as a dotted line on y equals 0. Okay. We'll do more precise graphing when we construct tables of values and plot points. Okay, but for now, we're just doing a quick sketch. Now I want to talk about the difference between linear and exponential functions. So take a look at each of these tables of values, and I want to know, do these have an additive rate of change, a multiplicative rate of change, or neither? So take a look at this first one. Each time n is increasing by 1. We add 1 each time. Where f of n, we're increasing by 2 each time. So this has an additive rate of change. This would have a slope of 2 over 1. This is linear. For number 2, while our n values are increasing by 1 each time, our f of n values, well, notice what's going on. From 4 to 8, we could say we add 4, but that's not the pattern for the next numbers, 8 to 16. We're multiplying by 2 each time. We're doubling every time. So this is exponential. For number 3, again, n increases by 1 each time. But take a look at f of n. Now we're going from 23 to 19. We're subtracting 4 each time. 19 to 15, 15 to 11. So again, this is still an additive rate of change, although now we're subtracting. Still linear though. Our slope in this case would be negative 4 over 1. For number 4, our n values are increasing by 1 each time. But our f of n values, we're going from 1 to 3 and then 3 to 9. We're multiplying by 3 each time. So this is exponential. For number 5, we're increasing from 3 to 4 and 4 to 5. N increases by 1 each time. And f of n, we're going from 8 to 4 to 2. We are dividing by 2 each time. So this is exponential. So even though we're dividing by 2, you can also think of this as multiplied by the reciprocal 1/2. So this still has a multiplicative rate of change, exponential. Number 6, our n values are increasing by 3 each time, so that's additive. And then f of n is increasing by 6 each time, so this is linear. This would have a slope of 6 over 3, or 2 over 1, or just 2. Now let's determine from the graphs whether they're linear, exponential, or neither. Now for number 7, this is a straight line. It's increasing all the time. This is linear. For number 8, notice what's going on with the graph. We decrease, and then we reach this point, and then it begins increasing. So this is neither. Both linear and exponential functions are either always increasing or always decreasing. Or for linear, it could also be constant. For number 9, again, this increases and then decreases and then increases, decreases, and continues. This is neither. Number 10, this is decreasing, but I can see that curvature there. And it looks like it's approaching a value. It looks like it's approaching 0. This is exponential. In particular, this would be exponential decay. Number 11, we got another straight line, but it's decreasing. This is linear. And number 12, this is increasing, and we've got that curve there. This is exponential growth. Okay. Got a few more for us today. Go ahead and flip the page. In summary, a linear function, the graph of a linear function represents a constant rate of change. A linear pattern is one in which the difference between any two y coordinates is the same. So linear models have a constant difference between any two y coordinates, whereas an exponential function pattern is one in which the ratio between any two y coordinates is the same. And that's that multiplicative rate of change. Okay, so this has been our notes on exponential functions